In the world of our scale, planets, humans, ants could follow Newton's law. If we know the position of something, direction and speed, we can determine its past and future position, ignoring the variables, of course. The billiard balls follow a predictable behavior, and everything else also seems to respect the laws of motion and Einstein's theory of relativity. Quantum mechanics can determine with complete accuracy the microcosm's behavior, but no one can explain this behavior. We can say that we enjoy the success that the theory had. All our digital technology is based on quantum mechanics, like many other relevant techniques, but microcosms behave in such a strange way that our shared sense is not able to understand. Well, what about the microscopic world? How do atoms behave, and subatomic particles? The behavior of the most basic units of nature can be considered schizophrenic. Subatomic particles can be in two places at the same time, behave both as waves and as particulate matter, and can go from point A to get to B. Before leaving, it can also go from point A to the B, C, D, E, etc. at the same time. Never able to determine with complete accuracy where you are and where you're going, a subatomic particle. If we know the position of an electron, for example, we lose the information of its direction and vice versa. There is always an uncertainty, Heisenberg uncertainty principle, in the microscopic world. To help the party, subatomic particles are in perpetual motion and may disappear from your room and appear in China or Jupiter instantly. Our universe seems to have two behaviors. Our range is predictable and boring, at the level of atoms is unpredictable and crazy. Scientists try to unify what we know about the macro and microcosms in a single theory, the so-called theory of everything. Some historical aspects. The fable above describes in a reasonable manner, albeit with some reservations, the status of physical after the emergence of quantum mechanics in its present form in the mid-20s. Perhaps the major difference is that, in the case of physics, there was no group of wise travellers giving us with a new weapon. A more accurate analogy would be to say that our friends just stumbled on rifles and found how to shoot by trial and error, while some of them, more astute than the others, prepared the attempted explanation. At this point in history enters the scene our friend Questionnaire, who in real life did not correspond to one, but various physical, which drew attention to conceptual inconsistencies and diverged from the prevailing view in different ways. Among them, the most notorious were undoubtedly Einstein, who never accepted the orthodox interpretation of the formalism of quantum mechanics, known as the School of Copenhagen D. There are no words to describe the resounding success experienced by quantum mechanics in the 20th century physics. It is surely the most successful theory in the history of science. Their results explain the nature of the behavior in dozens of different areas. Their MO forecasts verified by perfect experience, coming sometimes to reproduce the experimental data to the 8th decimal place. Its applied use is the basis of microelectronics, a science of materials, laser technology, modern chemistry. The behavior of light, metals, superconductors, organic molecules, atoms, nuclei, elementary particles obey blindly, and to this day do not know any limits of validity of the theory. In other words, the material world is, without a doubt, quantum. This state of affairs explains the indifference that the bulk of the scientific community nurtures the foundation issues. But at the same time, it emphasizes the importance of these because the fact is that the 60 years of its discovery, the most basic and comprehensive theory of modern physics, have not had their nature embraced by us entirely. Show that these difficulties are indeed severe and disturbing, and what the range of alternatives that we are the goals of this work. In the remainder of this opening chapter, we discuss briefly the conceptual assumptions that always adopted the elaborate physical theory. Then quantum mechanics is presented succinctly in its current formulation. Finally, to illuminate and highlight the oddities of the theory, we present and discuss these specific situations, thoughts and experiments where forecasts of the same actively violate our intuition and they even seem paradoxical. In the next chapter, when we discuss the different interpretation of the formalism of alternatives, we will use these situations to test them and shed some light on them. Like the last comment, I would point out to the uninitiated that the adjective quantum C, used to describe the theory, does not bring itself worthy any particular meaning of note and should be its use to historical reasons. Throughout this work, we will use the terms quantum mechanics interchangeably and quantum theory, quantum physics, and quantum theory. A little bit of philosophy. Almost all of us who are dedicated to the physics, mathematics or philosophy already had fun, at least once, with the solipsistic argument. It is that line of reasoning that says that the only reality of the world is your consciousness and all sensory bio-experienced, whether visual, auditory or tactical, a mere hallucination, dream even, generated by your mind. There is, therefore, no reality outside the material and independent of you. There are only your feelings and your conscience, and all illusory is the rest. The chair where you sit, the floor, your body, and all others. The solipsistic argument is fun for two reasons: to be unanswerable, and it fascinates. Also, since it adopts, it will not go any further. We stayed for a few minutes to laugh at imagining a discussion between two solipsistic, each firm or the other is only a hallucination of his mind, and then forgotten. There is not much to do when it is solipsistic. But at least in one aspect, solipsism is quite useful. It underscores the fact that the only unquestionable realities are my conscience and my feelings, all the rest being subject to doubt. Lest we fall in deadlock already mentioned, we need to go further and adopt the hypothesis that other people as much as I are also endowed with a conscience, feelings and thoughts. It is where the game starts, and once you choose this line, the following steps are necessary. How to explain the fact that two different people perceive the same things, at least apparently. That is, both claim to see and hear the same stuff, the book on the table, the barking of the dog, etc. The solution is to postulate the existence of something external to our consciousness, which is the source of those feelings which we both give the name of, say, book. Here it is appropriate to call the reader's attention to a question that often goes unnoticed. This entity whose existence just postulating is that it generates, somehow, the sensations experienced by us, but not to be confused with them. These two beings, although somewhat related, have different natures because this is a fact and that a hypothesis. Consider, for example, the fundamental note there, which is the sound wave of 440 Hz. That there is absolutely no connection between the musical note and vibration in the air is easy to see. If we can disconnect the acoustic nerve auditory region of the brain and reattach -10 in the area that processes visual information, every time someone plays violin near us, catch sight a flash or any other visual sensation. The analogous reasoning can be carried out with the electromagnetic wave of 5500 amperes and the feeling green H. We can, of course, argue that the links between sensation and matter are given at the level of nerve activity in the brain and not on the above. We end therefore by bumping the problem of mind-body relationship, which is a matter still open, not only scientifically but also philosophically. What we can do concerning this is to assume that despite having different natures, there is at some level a direct correspondence between sensations and a particular group of physical phenomena, e.g. nerve activity in the brain. According to this hypothesis, implicitly science always assumed consciousness is no more than a shadow of matter, an epiphenomenon, as the philosophers say, allowing us to limit ourselves to describe the activity of matter, whose internal dynamics only depend on itself, as we shall see. Starting from our consciousness, a level unquestioned fact, we decided to accept another's knowledge to escape the solipsistic doldrums. From this point we are led, almost inevitably, to adopt a series of hypotheses. The first is that there is something that produces various sensations, correlated minds. Matter, the concept substance. The belief is blind that the existence of something is independent of mind. The moon is there when no one is looking, or Neptune existed before being discovered. Moreover, we usually go further and make the hypothesis indeed quite high that mind does not affect in any way the matter, even though it affects the mind by definition. In other words, fully assume, as we have said, the idea that consciousness is just an epiphenomenon of matter. In terms of this conceptual framework, the science project becomes evident. It is simply to discover the laws, expressed mathematically, describing the internal dynamics of matter, and in possession of predict and explain phenomena, all of the nature. Since the rest, for our knowledge, are the observations and experiments, completed the total objective of science with the following assumptions: that the disturbance introduced by the measuring device in the observed system can always be made arbitrarily small, or at least inferred and calculated, and that the interaction of said apparatus to the observer's mind is safe. This is a particular case, this hypothesis exposed in the previous paragraph. It is the picture that always ruled classical physics, and for 3 whole centuries, the 17th to the 19th, was an absolute success. But it is far from obvious or compulsory conceptual framework, as it might seem at first glance. On the contrary, a large number of assumptions that have to be made, and all the guarantees their validity, their suitability to the facts. The science and physicists of the past were aware of this situation. That shows us the Helmholtz article, where part of this issue is discussed. But after all, how what was discussed here affects quantum mechanics? In fact, it is the opposite. How quantum mechanics affects what was discussed here. The issue in question in quantum mechanics is above all conceptual in nature, which does not mean that your solution brings verifiable news experimentally. Some proposed solutions, as you will see in the next chapter, involve the abandonment of one or more cases among those cited above. It is the case of contributions of von Neumann, Wigner or Bohr, among others. With these considerations in mind, let us now turn to the presentation of quantum theory in its aspects capital. The theory. The undoubtedly fascinating oddities of quantum mechanics stimulated countless disclosure attempts at a level accessible to lay people, the main features of the new theory. Such texts are quite common in newspapers, journals in science or basic physics books. The goal of all is always the same: to know the essential differences from the classical physics. Zero's points, in general, are focused or wave-particle duality, or the uncertainty principle, or quantum indeterminacy, or the apparent active role of the observer. However, it seems that none of these features is the most appropriate way to reach the heart of the matter. Another factor here plays a central role. Any physical theory consists of a set of statements, which we call laws, or NC, less than postulates P. Thus we have Newton's laws of mechanics, the laws of electromagnetism, the postulates of quantum mechanics. These laws define and relate the concepts involved in a quantitative manner, so that we can verify them experimentally. All this is commonplace for anyone connected to the technical area. The difference between quantum theory and other theories, which is nothing visible, lies in another point. It is the fact that these are all without exception ontological principles, i.e., its statements describe how the material world is, how it behaves. Behind these declarations, it is always an implicit model, picture, a hypothesis about how things are. On the other hand, is never said not a word about how to verify the laws and how to measure the relevant parameters. It is because in the classical theories to medicate the processes are always considered distinct, and in principle can always be done carefully so as not to interfere significantly with the experiment consisting of the art experimenter. Take, for example, Newtonian mechanics. Here the world is of material bodies moving in deterministic mode space, predicted over time. and interacting by mutual forces that can be described mathematically, forces such that alter the motion of bodies equally known manner. In the case of electromagnetism, there is also no doubt about the characteristics are, well, there are material bodies endowed with electrocargo loads that generate these space around well-defined electric fields, which in turn act on the charges alternating their state of motion and can, in certain circumstances, be self-sustained without the presence of loads constituting the so-called electromagnetic waves, which light is an example. In this respect, even the theory of relativity is no longer a classical theory. There is no doubt about how to observe the world, what are the observed objects, how to relay the data obtained by two observers. The only relevant question in this conceptual theory concerns the new status of the concept of time caused it. About what concerns us, it is as classic as the others. Let us return now to quantum mechanics. Early in the century, a series of phenomena, all connected in one way or another to the microscopic world, on the scale of atoms, challenged the scientific community to explain it using the known laws of physics. Initially, the situation appeared to be simply a case of inadequacy of the latter to the microscopic world, then simply find out which rules correctly describe the atomic level without contradicting the existing physical. But the reality was different in more ways than one. The physics community then was forced to admit that, contrary to what was assumed, that measurement process is not evident and suffers essential and perhaps irremovable restrictions, and therefore it was imperative, first of all, known the nature of these limitations. And so we come to the postulates of von Neumann of quantum mechanics. Unlike all other statements of physics, it is not a statement ontological, but epistemological, i.e., it refers not how things are, but what we can know about them. It certainly is the essential read best to understand what are the difficulties in the exegesis of quantum theory and is what we will use. Just one last clarification before we move on. Although historically have been developed to explain the atomic behavior, quantum mechanics has, as far as we can see, universal application. Another way of saying this is to affirm, in the light of the above, the limits to what we can know about a physical system are always the same, always obey the same rules, quantum mechanics, independent of the physical system concerned, of their nature, their ontology. By physical system, we understand any object or material entity, or a combination of these. An atom, a stone, into the water, a bacterium, a ray of light, etc. This universality of quantum mechanics is not a priori in contradiction with the fact that we do not realize in everyday life no limitation in our ability to observe and describe whatever it is. The only limits are those of practicability, the accuracy of the rule of the definition of the photographic plate, the microphone sensitivity, etc. We do not realize because, although there are, these limits are usually so subtle, so tiny, that unless the atomic scale, the above-mentioned practical limits are always more relevant, so that we can treat as the classic day objects a day. Later, we will see better how this happens. Anyway, we should accentuate the universality of the theory into question by itself at least one of the events that make up the standard framework: the lack of restrictions on the act of observing. We spent the actual content of the theory. We can say that it claims, first of all, the following. You find a measurement process is not unique, any a priori have can two or more, or even infinite different possible outcomes. That is, even depart the same initial conditions, it is not possible to predict in advance the outcome of an experiment. Similarly, even if a certain number of measures are taken in two physical systems producing identical results, we cannot conclude based on this fact that the two systems were in the same situation before you make the move. It is precisely this feature theory above we call quantum indeterminacy. The family of classical physics predictability disappears here, giving rise to a situation that differs significantly from what we are accustomed, despite the temptation, leave to discuss the possible reasons for this state of affairs when we analyse the various interpretations of the theory in the next chapter. However, one aspect of what has been said above may have surprised the most attentive layman. If quantum mechanics destroys any predictability of nature, how we want laws if they cannot predict anything? Quantum theory introduces the concept of the state of a system. If a physical state of an object, a system, understand its ontological status, i.e. what it is, how it is, etc., as quantum state, we are referring to its epistemological situation, i.e. to what we know about it, what we can measure, regardless of the nature of the system. The theory teaches us to characterize mathematically the quantum state of a system. With this, the theory says that 44 the likely results of any measures can be determined primarily from knowledge of the quantum state of the scheme. Moreover, we cannot determine in advance, as we have said, what will be among these the result obtained, but we know how to predict exactly what is the probability assigned to each result, i.e. with relative frequency that they will obtain if we repeat the experiment an infinite number of times. Similarly, just for that, we know the quantum state of the system. It is undoubtedly a forecast, and possession of it we can now get back to doing science. Consistency with classical physics is assured when we know that to apply the theory to measurement processes in classical cases, the possible outcomes with non-negligible probability are concentrated around the expected value classically, with a much smaller dispersion than the usual inaccuracies of measuring instruments. But the theory says more. It states that the quantum state of the system changes over time and teaches us to predict this change. It is necessary, however, that we can first find out how a given mathematical entity called evolution operator to carry out the prediction. It is precisely here that one finds perhaps the most important subtlety theory. Let's see. Up to this point, the presentation of the theory content, the epistemological status, quantum, and the ontological status, physical, walked parallel but disjunct, i.e. we are of course all the time assuming the existence of the physical system on which we may or may not know this or that, but we have not made any demands or assert anything about his physical description, the quantum description being made independently. We can certainly ask ourselves about the meaning of theory, i.e. in what ways the world must be, what ontology, which picture of the mind and matter can adopt so that there is no contradiction with the restrictions and epistemological rules just discussed. The evolution operator varies from one physical system to another. Nothing surprising in this, because the changes that he operated in the quantum state of the system reflected the changes undergone by the physical system, i.e. the action of the evolution operator is linked to physical processes themselves. In fact, that quantum theory does not conflict with classical physics. It is necessary that, by applying that to the processes of day-to-day action of the evolution operator play the traditional laws of physics. And indeed, so it is given in general. As in classical physics, epistemology superimposed on ontology, the verification of this limit, known as correspondence principle, is sufficient to ensure compatibility. But again, back to the evolution operator. It is an entity of the quantum formalism and, in principle, and nothing prevents us from just guessing its form, its structure in each case. However, there is certain method to build the corresponding evolution operator of a particular physical system, consisting of transposing, in the quantum formalism language, a particular physical system image. It works well, sometimes with subtle changes. It is the most explicit linkage of quantum formalism with the physical nature of the system, and must be taken into account when we carry out the discussion mentioned above. Concluding this section, we would like to insist that quantum mechanics, being an epistemological statement, in no way responds to the ontological question. On the contrary, it practically cries out for an anthology of the world to it coherent. It is precisely this that is the problem basics of quantum mechanics. 60 years after von Neumann's formulation of the postulates of quantum theory, his enigmatic partner has not yet appeared. Since then, we got what was overwhelmingly confirmed the quantum formalism, a brilliant career whose latest bid is subject to the third chapter of this dissertation. We also have in the meantime shown that the world, although not yet known exactly how it is, surely is not as we imagine it to be, as we shall see in the next chapter. The concept of state in quantum mechanics. In physics, it is called system. A concrete reality fragment was separated for study. Depending on the case, the word system refers to an electron or a proton, a small hydrogen atom or a large uranium atom, an isolated molecule or a set of interacting molecules forming a solid or vapor. In all cases, the system is a fragment of concentrate reality to which you want to draw attention. Depending on the particle can be inverted polarizations following neutral point. The specification of a physical system not only determines the values that experiments provide for their properties, or likely to measure these values in the case of probabilistic theories. Also, physical systems are not static but change with time, so that the same system, prepared similarly, can give rise to different experimental results depending on the time in which performs the measurement, or different histograms in the case of probabilistic theories. This idea leads to another fundamental concept, the concept of state. A state is a mathematical quantity, which varies according to the theory, which completely determines the values of the physical properties of the system associated with it at a particular moment in time. All the probability of each of its possible values are measured when it is an probability theory. In other words, all the information possible to know in a given system constitute their state. Each system occupies a country in a moment in time, and the laws of physics should be able to describe how a particular system part of a state and comes to another. In other words, the laws of physics should tell how the system evolves from state to state. Many variables that are clearly defined in classical mechanics are replaced by probability distributions in quantum mechanics, which is an intrinsically probabilistic theory, i.e., have only probabilities do not for a simplification or ignorance, but because that's all theory can provide. The state representation in formalism of quantum mechanics, the state of a system in a moment of time data, can be represented in two main ways. First, the state is described by a complex function of position of momenta of each particle renders the system. This representation is called wave function. Second, you can also represent the state by a vector in a vector space complex. This representation of quantum state is called state vector. Due to the notation introduced by Paul Dirac, such vectors are usually called cats. In short, both the wave functions and the state vectors, or cats, represent the states of a given physical system complete and equivalent form, and the laws of quantum mechanics describe how state vectors and wave functions evolve in time. These abstract mathematical objects, cats and wave functions, allow the calculation of the probability of obtaining precise results in a particular experiment. For example, the quantum mechanics formalism allows calculating the probability of finding an electron in a particular region around the nucleus. To seriously understand the calculation of probabilities from the information represented by the state vectors and wave functions, you need to master some linear algebra fundamentals. First, mathematical foundations. It is impossible to talk seriously about quantum mechanics without making some accurate notes. That's because many quantum phenomena difficult to imagine concretely can be represented without further complications with some mathematical abstraction. There are three basic concepts of mathematics, specifically linear algebra, which are consistently used by quantum mechanics. These are: first, the idea of an operator; second, eigenvector; and third, self-worth. Vectors and vector spaces. In linear algebra, a vector space, or linear space, is a collection of abstract objects called vectors that have some properties that are not thoroughly detailed here. For now, it is known that such objects, vectors, can be added together and multiplied by a scalar number. The result of these operations is always a vector belonging to the same space. The vector spaces are the primary objects of study in linear algebra and have various applications in mathematics, science, and engineering. The most simple and familiar vector space is Euclidean space bidimensional. The vectors in this space are ordered pairs and are graphed as arrows endowed module and direction. In the case of two-dimensional Euclidean space, the sum of any two vectors can be accomplished using the parallelogram rule. All vectors can also be multiplied by a scale that in Euclidean space is always a real number. This scalar multiplication can change the vector module and its meaning, but preserve their direction. The behavior of geometric vectors under these operations provides a good intuitive model for the behavior of the vectors in more abstract spaces which need not have the same geometric interpretation. As an example, you can mention the Hilbert space, where live vectors of quantum mechanics. Operators in quantum mechanics. An operator is a mathematical entity establishing a functional relationship between two vector spaces. The functional relationship which an operator sets can be called linear transformation. The more formal details will not be singled out here. Consider the Euclidean space. For each vector in this space to perform a rotation at an angle and find another vector in the same space. As this rotation is a functional relationship between the vectors of space, we can define an operator to carry out this transformation. Thus, two very concrete examples of operators are the rotation and translation. From a theoretical point of view, the seed of division between the quantum and classical physics is the use of operators. In classical mechanics, it is usual to describe the motion of a particle with a scalar function of time. For example, imagine that we see a flower vase falling from a window. At each time point, we can calculate how high is the vessel. In other words, we describe the position quantity with a number that varies as a function of time. A distinctive feature of quantum mechanics is the use of operations to represent physical quantities. That is, not only are the rotations and translations can be represented by operators. In quantum, mechanical quantities such as position, momentum, angular momentum, and energy are also represented by operators. Up to this point, it is possible to realize that quantum mechanics describes the nature of quite abstract. In short, states that a physical system can occupy are represented by state vectors, kets, or wave functions, which are also vectors, only the space of functions. The physical quantities are not directly represented by scalars, such as 10 meters, for example, but for operators. To understand how this abstract way of representing nature provides information on real experiments is necessary to discuss a last topic of linear algebra, the problem of eigenvalue and eigenvector. Principles. First principle, superposition principle. In quantum mechanics, the state of a physical system is defined by the set of all informations that can be extracted from this system by making some extent. In quantum mechanics, all states are represented by vectors in a vector space complex. Hilbert H space, thus, each vector in space H is a state that could be occupied by the system. Therefore, given two states, any, the algebraic sum, superposition, of them is also a state. As the norm, mathematics, of the state vector does not have physical meaning, all state vectors are preferably normalized. Usually, mathematics are called functional or linear functions associated vectors of a vector space, any to a scalar. It is known that the role of the vector space also forms an area, which is called double space. Second principle, measurement of physical quantities. For all physical quantity, A is associated with a linear self-adjoint operator, A belonging to A. A is observable, eigenvalue driver representing the magnitude A. Third principle, system evolution. If the system is not subjected to any observation, its evolution over time is governed by the Schrödinger equation. The most important conclusions of this theory are: in bound states, as the electron spinning around the nucleus of an atom, the energy does not change continuously, but discretely, transitions whose energy may or may not be equal to each other. The idea that states have linked levels of discrete energies is due to Max Planck. The fact that it is impossible to assign both the position and exact momentum of a particle resigning is thus the concept of course vital in classical mechanics. Instead, path, the movement of particles in quantum mechanics, is described by a wave function, which is a function of particle position and time. The wave function is played by Max Born as a measure of the probability of finding the particle at a given position and at one time. This interpretation is the most accepted by physicists today, the set of quantum mechanics assignments regulated by the Copenhagen School. To describe the dynamics of a quantum system must therefore find its wave function, and for this purpose to use the equations of motion proposed by Heisenberg and Erwin Schrödinger independently. Despite its formal structure ready since the 1930s, the interpretation of quantum mechanics has been the subject of study for several decades. The main thing is the measurement problem in quantum mechanics and its relation to the non-locality and causality. Already in 1935, Einstein, Podolsky and Rosen published their Gedankenexperiment, showing an apparent contradiction between tone and the measurement process in quantum mechanics. In the 60s, J.S. Bell published a series of relationships that would be respected if the city, or at least as we understand classically, persist in quantum systems. Such conditions are called Bell inequalities and were tested experimentally by A. Aspect, P. Grandier, J. Dalibard for quantum mechanics. As you would expect, such an interpretation still causes unease among various physical, but much of the community accepts that correlated states can violate causality in this way. Such a radical revision of our concept of reality was based on brilliant theoretical explanations for experimental results that could not be described by classical theory and include radiation spectrum blackbody solved by Max Planck with the proposition of energy quantization, experimental explanation of the double slit in which electrons produce a pattern of consistent interference with the wave behavior, comment of Albert Einstein's photoelectric effect discovered by Heinrich Hertz, which suggests that the light also propagates in quanta, defined energy packets, so-called photons. The Compton effect, which proposes that photons can behave like particles when their power is large enough. The question of the specific heat of solids at low temperatures, which discrepancy was explained by the theories of Einstein and Debye, based on energy equipartition according to a quantized interpretation of Planck. The resonant and discrete energy absorption by gases, proven in the Frank-Hertz experiment when subjected to certain electric potential difference values. The explanation of atomic stability and the distinct nature of the spectral lines, thanks to the Bohr model of the atom, which postulated the quantization of the atom's energy levels. The formal development of the theory was the work of real sets of many efforts and mathematicians of the time, as Erwin Schrödinger, Werner Heisenberg, Einstein, P.A.M. Dirac, Niels Bohr and John von Neumann, among others.